Okay. It's may I introduce Willem Heijltjes?
Willem. Yes, Willem.
Talking about the fundamental machine calculus screen.
Thanks, Johan. Yeah, so this is something I've been working on for the past couple of years. I've been dreaming it or daydreaming it. I have nothing else in my mind. You may have heard Chris talk about it too on occasion, sometimes, some of you. And this is the third installment. And it's called choice because we'll be talking about choice effects. But basically, I mean exception handling. So what's the functional machine calculus? A new model, well, still relatively new, for combining lambda calculus with computational effects. So there's, in the same vein as monads and call by push value, solving the same kind of problem. The aim of the whole thing, because the calculus is developing. It's not finished. I keep adding to it slowly. The aim is to maintain what I consider the main properties of the lambda calculus, the main properties that make the lambda calculus a good model of computation, and those are confluence, type strong normalization, and simplicity. Right? We have the lambda calculus is an extremely natural model of computation once you get your students used to the idea, that is. So this is the approach to doing that. We take the operational semantics as primary. That may come as a shock because we don't usually consider the operational semantics of lambda calculus primary. Because we think of lambda calculus as having beta reduction as primary. So we have a little shift in perspective there, and the reason for that is because it's easier to consider computational effects in an operational way, and it's much easier to base your design on in this setting, to do your design in this setting, and then make sure that you do it in such a way that everything else falls into play. So from that setting, the idea is to be very particular in what you add and don't add to your language. So you will see a calculus which has 6 constructors. So on average, so lambda calculus starts with 3. So I'm going at 1 constructor a year, or roughly. And then by the judicious choice involves choosing these operators, these language constructs, such that you can decompose effect operators in them. So you don't want to add a new operator for every effect that you can think of. Now you want to have good primitives, and then when you have a new effect that you want to incorporate, you check, well, can I already do this? All right. So previously, functional machine calculus 1 and 2 is lambda calculus with 2 modifications called locations and sequencing, and that captures mutable store, input, output, probabilistic or non-deterministic sampling, imperative sequencing, so sequencing of instructions, and encodes strategy, so it encodes call by value, monadic meta language, and call by push value. So that's what we had before. I will not assume that you know this, so I will explain all this as well. This talk, the new contribution here, is choice. So building on this basis, having these effects and this basis of imperative computation in there, the next question was, how do we deal with choice effects, or effectively things that are sums? So we're in approaching this, in my judicious choice of primitives, I wanted to find something that could capture all these things naturally, because these are all things that I could think of that semantically are sums. So exception handling is done in Haskell, which I'm programming in, with the exception monad, which is an error value summed with your return value. Constants are generally modeled as sums of unit values, and these expand to data types, but I'm not adding recursive. Recursion is a different thing, recursive types, so we're sticking with just plain data types. And basically that is very similar to just constants. And iteration, if you have an iterator, a loop, as it were, that's something semantically that takes a map from A to a sum. So from A you return A or you return B, to an iterator on A that, so it takes M, computes M. If M exits with A, you keep going, you iterate again, you go back into iter, and if M ends at B, you exit. So the A disappears as an exit value, and this categorically perfectly dual to recursion. Alec, did you do that in your paper with Plotkin? You did the categorical version of categorical fixed point construction, and this is just dual to that. Well, it just works. I mean, this what is this, Blumenestic or something? Anyway, this is known as iteration generally, but it's just a while loop. Okay, so I wanted to include these things. Here's the how all this fits together. We start from lambda calculus, focusing on the operational semantics, the machine, and this is just the Krivine machine, except I am using substitution instead of environment. I want to keep this as an operational semantics, not as an implementation model. So the first thing I do is I change the syntax to emphasize the machine idea. So the machine has states which are a term and a stack. So terms are evaluated in the context of a single stack, and an application pushes its argument. So square brackets n means push n onto the stack, and an application pops its argument as x. So these angled brackets mean pop and substitute whatever you popped for x in m. Simple Krivine machine. And so this is the formal definition. I write my translations top to bottom, so that it's easy to see where things go. And that's it. The reason to change the syntax is both to emphasize this operational behavior and to allow all the things that I'm going to subject the calculus to, all the extensions, to fit neatly into this syntax. So this is our lambda calculus. And the first extension, called locations, is to simply say, well, we have one stack, why not have all the stacks? We allow any number of stacks on our machine. We name them in a set of locations that includes lambda. So we keep our lambda as sort of a pointed set. So we have our original lambda location, and now we can have any other number of stacks indexed in a set of locations. And then we parameterize our push and pop to indicate which stack they're operating on. So just a set of stacks directly accessible, and you can already see what this is doing, right? This is giving you random access memory. We're conservative. We want to keep our lambda calculus in there. So we, whenever we use our original lambda location, we simply omit it so that the syntax doesn't change. So this is a shortcut for the lambda thing. Good. Now, what does this look like formally? We keep our stacks, but our states now have a family of stacks, and I call that a memory. And a memory is simply a family of stacks in locations. And we can keep this accountable set, and where only finite with finite support and anything you can. It doesn't matter if you have an empty stack. That's the same as not having it. So we can ignore that. So then this dot here separates one memory from indicates isolates one stack from the memory. So now our push operation pushes onto the designated stack A, and our pop operation A pop X pops from the designated stack A. And that's it. What can we do with this? We can model what we've called reader-writer effects. So input-output, probabilities, and we model probabilities and non-determinism as well. And we model these in the same way that as though they were inputs, right? A stream of non-deterministic or probabilistic Booleans. So we take 3 locations in input, in for input, out for output, and random for the random number generator. And we encode a read term, or we can read from input by saying, well, we pop from input and we use it. We can print n to output and continue as m, and we can pop a random value and bind that as x in. Yeah. But so this is simple, right? Just accessing your stacks. You can use stacks or streams in there. The machine doesn't really care. But the real thing here is combining these pushes and pops to get state updates. So we've a mutable variable is simply a chosen location for which you then have an update. So update A with n continue as m is encoded as pop and discard. So this is a Haskell style underscore is an unused variable. So pop and discard, push n to A and continue as m. So we've updated by popping, discarding, and pushing. And lookup is popping from A, whatever it was, as x, restoring what this value onto A, and then using it. And this turns out to be the way that Haskell mvars used for what's it, shared memory concurrency work as well. And then they further observed that you can use this as a natural locking mechanism, right? If you have two competing processes reading from memory, the one that pops first leaves this state empty and just locks the process. So what we get with this is, well, confluence for this calculus, for this interpretation, means that you have a sound notion of reduction equivalence. You can, right, a confluence reduction relation can be seen as an equivalence, and that includes algebraic store. So we get the laws of Plotkin and Power for free, and type termination for higher order store. If anyone's familiar with Landon's knot, this uses higher order store in a typed way to encode recursion. This can no longer be typed. Yes? Okay. What we've seen thus far is strictly limited to call by name. So it's limiting as a programming language, and that's because we've made it confluent, right? So making it confluent means we've fixed our evaluation semantics, and now we need to include strategies. But also, this is a very natural thing to do. So we have a machine, a stack machine, that operates sequentially. When you have sequential operation, you want an identity and you want composition. So introduce identity and composition, skip and sequencing. This is exactly what you would expect from an imperative language. And we will use the standard implementation. We add a continuation stack for the rest of the computation, and m sequence n pushes the remainder, and skip, when you're done, you pop to do the next part of the computation. So what does that look like? Now our states have a memory, a term, and a continuation stack. And a continuation stack is just a stack, except I write it the other way around, so that everything is horizontally nice and tight. Continuation stack does nothing for pushing and popping, but of course it works with sequencing. So sequencing pushes the second term onto the continuation stack, skip, pops, and evaluates. Standard, but note how this is, these stacks, the memory in the stack, they're orthogonal, they're independent, right? So you get these, you can add these things in a modular way. What do we get from this? We can embed call by value lambda calculus. Values are embedded as is, but then if you embed a value, if you view a value as a computation, it is returned. So you get this new construct. You can do something new here. Because you have a skip, a do nothing, you can push your value to the stack as a return value and terminate. We didn't have that before in lambda calculus. That's a new thing. And you use that to encode call by value behavior. And this is the expected behavior, right? When you have your have a value, we've reduced your term to a value, you're done, you return it. And then an application evaluates the argument. So this is evaluating the argument before the function. So you evaluate the argument first, and that will push some value into the stack. You evaluate the function, which will push another value to the stack, and then you pick up that last value and execute it. This will give you basically the behavior of Landin's sect machine, a CCD machine, encoded in the term running on the Graphene machine. And then if you look at the monads, the return, it just does that. It does the same trick as a call by, as a value and call by value. It returns, it pushes the term onto the stack as a return value. So this is generating, as it were, a local call by value behavior. And monadic bind, which evaluates M to a return, is sequencing. So we evaluate M until it returns, or this return, I mean, and then we continue by popping the result and continuing as that. So we get a nice, simple operational interpretation of the computational meta language, and the call by push value constructs follow this same pattern. And you can start to see some similarities with call by value and how these things can be considered to fit together. So here's the new thing. So we have introduced two new aspects to lambda calculus: imperative skip and sequencing. And the sequencing I've seen before in a number of calculi. The skip I've rarely seen, which is interesting because it's very important. It's what signifies successful termination on the machine, right? Before we had a machine that could run and it could terminate, it could end. But now we can terminate with an explicit notion of we are done. Okay. Now, suppose we want to think about choice effects. So, in particular, exception handling. Instead of having just a skip, we generalize to having any number of exit codes, right? So think of a bash script, right? It can, or any program that has this feature that running on the terminal, it runs and it gives you an exit code, right? An exit status. We do the same thing. And this is, so we generalize our sequencing, our skip, I mean, by saying, well, we do exactly the same thing as we did with the stacks before. So instead of having one way of terminating a program, we allow any number of ways of terminating a program, including success. So we have got success and a number of jumps or exit codes. And then we add that to sequencing to become conditional. So sequencing, or a join, says evaluate M, and if it exits with J, then continue as N. Otherwise, we discard the continuation. And again, this is, we make it conservative by taking the skip was already there. We kept the skip and we write sequencing for continue with success, join with success. Okay. In isolation, the generalization on the machine looks like this. We had our sequencing implemented as pushing onto the continuation stack and popping from the continuation stack. And now this becomes conditional. So continuation stacks become stacks of conditional terms. So K is a sequence of jumps that yield terms. And that is then pushed onto the, so a join pushes that continuation, that conditional continuation on the continuation stack, and a jump selects or deselects the next continuation. what can we encode with this? Well, this is just exceptions, right? It is literally exceptions. Throw an exception E is just E as a jump. And try M, catch E with this, catch an error E with N is this. That's what we have here. Using that, we can encode Booleans, for instance. Booleans are just jumps, and a conditional, if B then M else N, can be encoded by do B, catch the top with M, and then catch the bottom with N. So the parenthesization is like this, is associated to the left. And there's a bit of a caveat here. So if your M ends in a Boolean in a false, it will jump to the N. But let's assume that M ends with success, right? Which we can, as soon as we put the argument stack back, we can always arrange that. And any constants are jumps in that way. So a case construct becomes evaluate M and test against each jump in turn. And again, we assume that the ends don't end in any of the C's, so that there's no conflict there. And now we add iteration. So the fall through nature of this, right? The conditional nature of these exceptions means we can do loops in a very, very nice way. So M to the J repeats on J and exits on other jumps. So on the machine, M loop on J evaluates M and pushes J to M to the J on the continuation stack. So that will keep on looping until at one point M exits with something that isn't J. So now this is an actual do while loop. So do M while B, where B is a Boolean, is encoded by saying do M, then do B. If it's true, keep repeating. If it's false, terminate successfully. But we do need to capture the exit jump. So the Boolean generates a repeat jump, which is top, and an exit jump, which is the bottom, and we need to catch that in order to signify success with this computation. A normal while loop is while B. We can encode that in a normal way. So first do B, and if it's true, then do the loop, the do while loop, and catch the failure. And this catches both failures, that B and that B. Or we can be clever and we can do the Boolean first. Then on top, if it's true, we do M and we repeat on success. So we assume M ends in success, then we repeat. And otherwise, if B is false, then it will skip M and it will go straight here. So what we've done here is we've used our bots as a break. So breaks are also jumps. We've got a notion of loop that involves breaks, and you can encode a continue as well, etc. And this is the full calculus on the stack machine, and it's simply putting back the memories in there and putting back the operations on memories. I'm gonna have to skip this. So we've got data constructors as well. Nice, but let's do our example. So here is a rendering of factorial in a call by value language. Well, in an imperative language, right? This is how you would write a factorial in, well, maybe not Python, but something like Python. But we can encode all these things on our machine. We can assignment we can do by a call by value assignment means evaluate M, then pick up the return value and update A with it. And A, as a mutable variable, is pick up the value from A, restore it, and push it onto the main stack for use. A variable X becomes return X, just as we did with values in call by value. We can do multiplication. I am assuming constants. You can encode constants, right? You can encode multiplication with jumps. It's not very efficient. So we'll assume that we just have a primitive for that. So multiplication, call by value, means evaluate M, then evaluate N, and multiply the results. We have our while loop from before. But now we assume that M returns a Boolean on the stack, so we have to pop it and evaluate it, but otherwise it's the same. And we can make function definitions simply as radixes. So this is lambda calculus, right? Just lambda calculus. Okay. I have a bit of time to explain types. I'll try to be quick and leave some time for questions. So the whole point of this was to get the nice properties of the lambda calculus. And I'll quickly show you how types work. For the fragment of lambda calculus with sequencing, which is the easy and nice bit where the novelty is really, a type is of this form. A vector of input types implies a vector of output types. Semantically, this is just a product, and the arrow is just an implication. So you get a stack, a vector represents the types of a stack, you get a stack, and you return a stack. And it just indicates the machine behavior. So formally, types are implications between type vectors. Type vectors are sequences of types. The meaning here is an arrow, and this is a product. And the meaning of the whole thing is if M has type sigmas to taus, and we have a stack of sigmas, then there is a stack of taus such that the machine runs successfully. That's the meaning. And with that meaning, you get, and with the right axioms, you get a strict Cartesian closed category where the objects are type vectors, product is concatenation, the arrow is closure, and the skip is the identity, composition is composition. We have a terminal and a diagonal. So if we have a Cartesian category if we restrict it in a certain to a first order calculus, and evaluation and eta are these terms. So these take a variable, and so they take something from the stack and evaluate it. That's eval, and this one takes a bunch of inputs and puts them as a vector on the stack. So this is a different model from the Lambert and Scott model of Cartesian closed category. Right? This is not the same. If you take the fragment that's lambda calculus and look at that, and so that's a different thing. And it's sort of a bit of an open question. I've started thinking about this recently, what the relation is between these two models, but maybe, but I think someone with more category theory than me would like do this on a napkin at the over dinner tonight, maybe. Okay, very quickly, skipping all that, just to show you how choice types work. So we can get memory types simply by parameterizing further in A, so vectors, a family of vectors, and we get choice types by parameterizing these memory types into J. And the semantics is a indexed product and an indexed sum. So we have a nice duality going on right there. And the meaning, well, the meaning is simply the machine runs as expected. Right? Given an index, an input memory, the machine runs and gives you some return memory indicated by your family. Okay, let's see if and with that, you can type your factorial. So Booleans become input memory to a sum of output memories, the same. Booleans work, but capturing this changes one of the output, one of the return, one of the exit values, and what you get for factorial as a whole is factorial takes in a value, takes in the value at the accumulator location A, takes in the value at the counter location Z, or the counter location Z, C, and returns the same with success. There we go. Yes, yes, there, done, done.